Greetings, everyone. I, Saatvik Sumanta, with my team members Denesh, Abigna, and Abhigyan, team ID team 592327, is here to present our deep learning model for disease detection in tea leaves. Here we have tested three models. One is a standard convolutional neural network, other one is a VGG16, and the last one is a ResNet 50. Here we show in our Google Collaboratory notebook the outcomes of the three model testings, and in the end we display the final model which has been used for our backend deployment using Flask. So I will just screen share and show you my Python code in which we have executed our CNN model. As you can see, here we have executed our CNN model. First, we have imported our tea leaf diseases detection dataset from the Kaggle using the Kaggle API. As you can see here, we have applied pip install and then made a Kaggle directory where we used a Kaggle token from our account to access this API. Then using the API, we have downloaded the dataset. Then we unzip the dataset accordingly. Now, for training of the model, we need a train and test split. So we create a train test split directory where we store our test and train and validation folders respectively. To divide the data into test and train or test and validation, the validation word and testing word have been used replaceably in the context of our machine learning model, as we are using only a testing and training and testing splits. The training split is of 80% and testing split is of 20%. So using a split folders library provided by Python, we have split our data into 80-20 ratio. And then we have imported necessary libraries such that we can execute our CNN network, for which we have imported NumPy, Pandas, Matplotlib, OS, PIL, TensorFlow, Keras, Layer, Sequential Classification Report, and Pathlib. All these models have been used in the upcoming CNN network in order to facilitate various utilities. So to train a model, we first load the dataset in a dataset directory. Then we make sublists using this dataset to check the labels available for us. We have 8 classifications: red leaf spot, algal leaf, gray light, healthy, brown blight, anthracnose, bird eye spot, and white spot. Now we check total number of available images in these label folders. So as you can see, there are 143 images for red leaf. Algal leaf has 113 images. Gray light has 100. Healthy has 74. Brown blight 113. Anthracnose 100. Bird eye spot 100. And white spot has 142 images. Now we define our parameters to train our model on. So first, the training batch has been set at 128 size, and the validation batch has also been set at 128. The image height and width have been set at 224 pixels. The image size has been declared with image height and width parameter. The validation split or the testing split, which can be used interchangeability in our video for the CNN model, is 20%. Then now we are loading the training dataset. Then we upload the validation dataset, the testing dataset. In the training dataset, there are 708 images, and in the testing data, we have 177 images. Then we again check the available labels in the training data, and then as you can see, the following 8 labels or eight labels and the 8 images are shown here. One first case is the anthracnose, then is the red leaf spot, also known the red leaf spot, gray light, white spot, brown blight, etc. These photos were generated randomly from the labels. Hence, you might see a repetition of some images, like gray light has been repeated twice because these images were selected randomly from our dataset. Talking about data pre-processing, The data processing has been done with TensorFlow Autotone in order to preserve the pre-processing time so that we can expend it on our model training. From now, Dinesh shall take over to explain you about the CNN model building.
So coming to CNN model building, in our model we have used the data augmentation layers. Uh, in data augmentation, which is using TensorFlow and Keras for image classification. The key components in the data augmentation layers are the data flip, random flip, random rotation, and random zoom. For random flip, we need the images flips horizontally and vertically during training for additional variations. And random flip vertical, as it the name says, it flips vertical, and the random rotation 0.2 applies a maximum angle of 0.2 radians. Random zoom is that the image zooms into the images with a maximum zoom factor of 0.2. And coming to model architecture, uh, the key components in this model is that we have used rescaling. The rescaling factor normalizes pixel values from 0 to 255 to 0 to 1. And the con 2D factor is that this keyword is that the 16 filters of size applies to 3 into 3 convolution with the ReLU activation that maintains input size, and the max pooling 2D operation for downsampling. The above convolution and the max pooling layers are repeated with increased filters and reduced spatial dimensions. Flattens the output into a 1D array for dense layers. The dense 32, activation equal to ReLU is a fully connected layer with 32 units and ReLU activation. And dropout 0.3 is a dropout layer with a dropout rate of 0.3 to reduce overfitting. And batch normalization is nothing that normalizes and scales the input for improved training stability. And then the model ends with a dense layer having num classes units, where num classes represents the number of output classes, 8 in this case, and uses logics as input. And this is the compilation model compilation. Uh, the three important factors is which is used in which is used to import is that if keras.optimizers.atom. Atom optimizer is used with a specified learning rate, and sparse categorical cross entropy loss is used since the labels are integers. Metrics equal to accuracy. The model's performance will be evaluated based on accuracy during training. This set of code actually aims to enhance the model's ability to generalize by using data augmentation techniques, improving its performance on unseen input data in the data set, which are the images. And this is the CNN model summary, which we get the basic information about the code like sequential scaling and like all the components we have used above code. We are coming to the first step of the entire model, which is second step actually, training. In this, this is the main part where we get the accuracy of the model. In this set of code, the code trains CNN model for a specified number of epochs, 300 in this case, using the data set we have provided, and it will evaluate its performance on a validation data set. After training, it visualizes the training and validation accuracy as well as the training and validation loss over the epochs. And we will also be finding the accuracy using matplotlib to visualize the model using plot graphs. In this set of code itself, the CNN model is trained using train ds as the variable and validated using the validation dataset val_ds. The training process runs for 300 epochs, meaning the entire training dataset is passed through the network 300 times. And we need to store the trained data set, train history. During training itself, the model's accuracy and the loss are calculated for both the training and validation data sets after each epoch. The training history, including accuracy and loss values, will be stored in the history variable, and that is why we have used assign operator to history, where all the loss and accuracy will be values will be stored in history itself. And coming to visualizing training and validation metrics, the code then extracts the accuracy and loss values from the training history for plotting, as we have assigned to the variable history. It creates a 2-into-1 grid of subplots for visualization. In the first subplot, it plots the training accuracy and validation over the epochs. This helps visualize how well the model is learning from the training data and how well it generalizes to unseen validation data. In the second plot, it plots the training loss and validation loss over the epochs. This shows how the error of the model changes during training and validation. Visualization, when coming to visualization, the plot show function displays the two subplots as a single figure, allowing you to visually assess the model's performance over the training period itself. The x-axis represents the number of epochs, and the y-axis represents the accuracy ranging from 0 to 1. And loss, when coming to loss, a numerical value indicating how far off the predictions are from the actual values. By looking at these plots itself, you can gain insights into how well the model is learning from the data. High training accuracy and low training loss are good indicators, but it's essential to ensure that the validation accuracy and loss are also favorable, indicating that the model is not too overfitting. Certainly, the this part of code is model evaluation, which is the third stage of the image classification. The codes, this evaluation is used to evaluate the trained CNN on batch of images which we upload, from which the data set we have uploaded earlier. This happens, the multiple processes happening in this code itself. First is retrieve a batch of images in the data set. It retrieves a batch of images and its corresponding labels, which we assign during training process, and making predictions. The CNN model predicts classes of the images in the batch using the predict on batch function. Now, after making prediction, we should convert those prediction into class labels. This set of code converts the raw model predictions into class labels. For each prediction vector, it finds the index with the highest value using np.argmax to determine the predicted class for each image in the batch. And after converting the prediction, we should print the predictions and labels, which is important which is considered as an output. Then after prediction, it prints the predicted label using class prediction, which is used in here. This is the class predictions.i, which after predicting, it prints the class labels and the actual class labels, which is assigned to a variable label batch. After printing, generating classification report, the code this report provides metric like precision, recall, F1 score for each class, giving a detailed overview of the model's performance on the batch. And we come to the last stage of the image classification, which is the model testing. We come to model testing again. And after we run multiple epochs, around 300 epochs, we get a testing accuracy of 82%. Now we use a TensorFlow.keras preprocessing for image loading and preprocessing. The code first loads image from specific file paths and resizes them to match the input size expected by the CNN model, which is 224 into 224 in this case, 224 pixels. The images are then converted into numerical arrays suitable for feeding into the model. using functions from the image model, IMG model. And then here happens the model prediction for the testing process. For each image IMG, like IMG1, IMG2, IMG3, the code uses the trained CNN model, which we did earlier to make predictions. The predict function, the predict function of the model is used here. This function returns a probability distribution over the classes. np.argmax, which is mentioned here, is applied to the prediction output to find the index of the class with highest probability, effectively determining the predicted class for the input image. The predicted class is, as I said earlier, the predicted class is used to obtain the corresponding class name from the OP list, which is the OP is a list where all the um, leaves name, the tea leaves names are mentioned, and the predicted class is used to obtain the corresponding class from the list, from the OP list. And then coming back to predictions and labels, display this, it is important to display the predictions after training the code, training the model. The code then prints the predicted class for each image based on the model's output. For example, it determines, for example, if an image is classified as healthy, for example, if the image is classified as algae for any other class forms from the predefined categories. And then we should create a data frame for comparison, and the code creates a data frame containing the actual labels for within the variable label batch and the model's prediction under label class predictions from a previous batch of images. And this set of code allows for easy visual comparison between the true labels and the model's prediction. So overall, the CNN model building, in summary, the model demonstrates how to use the trained CNN model to classify the images into predefined categories. It loads the images, process them for the model output, predict their classes, and then compare these prediction with actual labels, providing a convenient way to access the model's performance on new unseen data from the data set. And this is the plot after a comparison of the predicted data. And we are supposed to save the model from which we obtained from training, from the training and testing and evaluating the model. There are actually multiple ways of saving the model. The first way is that we have actually used both ways. The first way is that saving the file as h5 file, and another way is saving the model as pickle file. And for in order to save the file in pickle file, we are supposed to import pickle library, and then we can carry out TensorFlow, or we can carry out TensorFlow libraries to save the model as pickle.
My name is Abigna Kotamareddi, and I was part of the project Tea Leaf Disease Detection. And I was in charge of testing other models, and I chose to do VGG16. So firstly, I imported the libraries required, like VGG16 and the layer libraries. And then I removed the top layer, last layer of the model of VGG16. And then I checked all the model layers of the VGG, after which I froze the pre-trained layers of the VGG layers, after which I added two layers, one of which was the output layer and the other one was a flattening layer. After which I declared the VGG model and compiled the model. And then I imported image data generator to create the model. So firstly, I defined data generators for train and validation sets, after which I defined the batch size as 15 and image size. And then I created the data generators, train generator and val generator. And then I trained the model with validation. So After training the model, the difference in accuracy between training and validation, which I got, was 7.33% or 0.0733. And then I checked the model evaluation, wherein I got the test accuracy as 50%, which is comparatively lower than CNN, hence why the model was dropped.
Hi, I am Abhigyan Ghoshal, and today I will be explaining about the ResNet 50 transfer learning model. First, here we import the necessary libraries. Then we talk about the architecture of the ResNet 50 model, including the shape size of 224 by 224. And here we talk about we check the layers of the ResNet 50 model. Here our total amount of layer is 175. In the next line, we add this layer dot trainable equal to false, which means that the value of the pre-trained data will not be changed. Then here we add the flattened layer, in which the output comes into the dense layer. And here is the summary of the ResNet 50 model. Total parameters, the trainable parameters and the non-trainable parameters are given here. Then we compile the model and we get an training accuracy of around 88% and the validation around 68%, which is somewhat overfit. And here in the graph, you can easily see that the training and validation accuracy are not in sync, and we are suffering a huge loss in the training and validation loss, this graph. And after that, in the model evaluation, these are the predictions and these are the label. And total 8 classifications are there. And you can see these are the images of the random data we chose. And now after testing on the random data, the ResNet model shows a testing accuracy of 13% and the training accuracy was around 88%. So this is like a huge overfit. So after this ResNet 50 model gets rejected. Now Saatvik will explain you about the website working.
Welcome all. Now we shall discuss our back-end execution of the machine learning model in our web app using Flask, and the front end has been developed using HTML, CSS, and JavaScript. Let me screen share and present you our project. As you can see, here we have presented our web app, which has been developed using CSS, and see that you can submit your test photographs and the results. Types of classification which we are able to do, as also explained earlier, are leaves, algal leaf disease, chronos, bird eye spot, brown light, white spot, red leaf spot, gray blight. Earlier you might have seen this as gray, but it was found in our further searches that it is gray blight. It was a spelling mistake inside the Kaggle dataset. Hence, it might have been referred earlier as grey light. To apologies for the mistakes done before. Now we shall move on to the model prediction. First, we try to choose the file. Let's take a sample leaf from our, which has been labeled as, first we check with a healthy leaf. So we load the format, then click on predict. The model is now in the server. It has been on our system, and I can see the machine learning model has perfectly classified our leaf into healthy. Now let's again test this model. Let's choose another leaf. Let's take brown blight for this testing. and now the system is running, and the final outcome is brown. You can see. So the model has been working perfectly. Now let us go to the Flask code and try to understand how it is. Let's go to the HTML code before the Flask. As you can see, we have started with our HTML code first. So we first declare the HTML tag, which is usually done to start any HTML document, and then the basic commands are declared to make it a universal HTML page. The falling leaves animation has been just given as a title because there was a leaf animation running behind the screen, as you might have seen earlier. Now we declare our CSS style, which has been executed to beautify the page. Coming next, we have declared a body. Here is a title, convolutional neural network based tea leaf disease detection, which was seen in there. We have described a model in this paragraph. And then, as you can see in this, a table has been created as the images seen aligned perfectly. It was done using a table tag of the HTML. So in the table, we have created two rows with two rows and four columns. In each cell, image is being displayed. The image source is using the Flask format, which is URL for, and the images are kept in a folder named static, and the HTML page name index.html has been kept in a folder named templates, and where the Flask is able to read this image file from the static folder. So these images have been shown using these table commands, and then we present in the form, which is used to upload an image for the testing. The form takes the image input as a variable named as image. So this image stores the binary value of the said image which has been uploaded by the user, and then it is transferred to the Flask app. In the Flask, there are mainly NumPy, Pandas, and PIL with Pickle. In the Pickle, the model is used to load. The CNN Pickle is read binary. Then we start the app and render our HTML page. Then from the post method, we collect the data which was stored in the variable image and then start reading it. If there has been an image uploaded, then we return the predict function. And if there is no image uploaded, then we return no file uploaded message. In the predict function, we create a variable for this Flask app as an image, and which reads the image values from the form which has been used by the user to upload their target image. Then this image using the PIL library is resized into a 224 by 224 pixel, because our CNN model has been trained to read only 224 by 224 pixels. Then this 224 by 224 square image is converted into a NumPy one-dimensional array, a one-dimensional vector array. Then it is expanded accordingly, and then it is sent into the model, as you can see, np.argmax model.predictx. So the x value from the image which has been converted to an array is now being transmitted to the model. The model then processes it as per its training, and it has options of 8 options it has shown in this array. And then the model, once it chooses the final value, then it sends the prediction variable as shown in the HTML document. Here you can see the prediction variable. The backend Flask code sends this prediction variable from this list to the HTML page, which then renders it as one of the option as healthy, anthracnose, etc. So that's how. And then and in the back front end, the JavaScript code is also running to produce the leaf animation which was seen earlier. So we thank you for your patience, and this was our presentation on tea leaf disease detection using deep learning. Thank you.